Okay, here we go. We've got aluminum now, aluminum solid. So I'll put an S here, aluminum solid. And let's say we have 10.0 grams. Now here we have an equal mass of iron solid, and we have 10.0 grams. Here we have an equal mass of liquid water, 10.0 grams of liquid water, so that's H2O liquid. Okay, so we have equal masses of three different substances. Now be careful, different substances have different specific heat capacities, so don't start saying specific heat capacity is 4.184 for that, because it's for this only. You pizza lovers, you pull a pizza out of the oven. Why is it that the cheese might seem a heck of a lot hotter than the crust? Because they have different specific heat capacities. They're gaining and releasing heat at different rates. Well, let's go ahead and add. Let's go with 300.0 joules of heat. Let's add 300.0 joules of heat. Okay, let's add 300.0 joules of heat. Starting temperature. T1 is the same for all, so let's go with 25.0 degrees C. So T initial equals 25.0 degrees C. Here's our famous formula. It's famous now. Q equals ms delta T. Okay. Let's see. We need to get the specific heat values here. So S equals 4.184 joules grams times degrees C. Let's see. Aluminum is 0.999 joules per gram times degrees C. So this is S. Okay. Big difference in specific heat capacity. The iron, I believe, is 0.444, and it is, just confirming. So the iron S equals 0.444 units joules per gram times degrees C. So notice, big difference. When you were freshmen, we said water has a high specific heat capacity, which means it can gain and release heat without a big change in temperature. So look at the high specific heat capacity compared to these two metals. Big difference. So we'd expect this to gain and release heat without a big temperature change. That's what we'd expect. Let's do the math though. expecting is one thing, but let's do the math and let's get the final temperature for each of these. We have equal masses. We have equal amount of joules input. We know that this is Q is positive. Do the write the formula, show the algebra first. So that way the grader will give you a bonus, well, not a bonus point, but will give you a point, maybe, even if you have a wreck halfway through the question. I'll be like, oh, well, they knew what they're doing. They got started. They knew the right formula. They did the algebra. Then they plugged it in wrong. So don't let that happen. Somebody at home, quick question, Cam fan. Is the final temperature going to be higher or lower than the initial for all three of these?
Higher.
Of course, yeah, absolutely. Because this is an endothermic process where the system is absorbing energy from the surroundings. What is the system? The system for all three are the liquid and the two solids. You guys need to be meticulous, show the canceling. I'm going to just give you the final. I'm just going to plug and chug here and get you the final answers. But you guys show the canceling. That's why I'm giving you specific heat full units. So that is a good problem. It also, well, I'll let you finish, and then check your work again. I didn't, I could plug in 310 and then 0.414, and then I want to see you canceling and so on and so forth. We like our final answer to be boxed so we can get right to the chase. Kind of interesting. Notice heat and temperature are not the same. Same amount of heat input for both, but the change in temperature is quite a bit different. Notice water absorbs fairly large amounts of heat and has a relatively small temperature change to many, 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 many other substances. On a practical level here we go, practical level. Let's go, oh, and by the way, don't forget, my answer, I have to take points off. Why? I did pretty good, though. If that's a 6-point question, I get at least 5 points, maybe 5.5. Why am I taking points off on my work here? Didn't I ask? Maybe I didn't. I thought I did. Didn't I ask for the final temperature? This is not the final temperature. That's a change in temperature. The final temperature we have to add to 25, add to 25, add to 25. Okay? So write that off to the side. Make sure if we're asking for, and you guys go ahead and write the final temperatures. Shoot, I thought I got 6 out of 6 and I went home. I was high-fiving Ethan. We went to sports practice. What practice we go to? We went to soccer. Sorry, I played like 3 years before it was popular. And I got 1 goal out of 3 years. And you would have thought I won an Olympic gold medal. The way that I charged off that field and then started jumping on people. And we were right in the middle of the game. So the coach is like, get back out there. So I'm just overly excited. But anyway, we're talking at practice, and I'm like, yeah, I aced that. And he goes, yeah, I aced that too. What'd you get for aluminum? Oh, I got 55. What? 30 was the right answer. Oops. You did get it right. I missed one here. Okay. On a practical level, watch. Let's go back to 25 degrees and add this amount of heat. So I don't want to get burned here. I don't want to start on fire. Practical level, look at what we're doing. I'm touching both as we're adding that heat. Temperature's rising, rising, rising. Ow! Sorry to stir you up at home there. Look, though, why can I keep my finger in this? No problem going up to, I'm still going to be under body temperature here. Well, there I skyrocketed to a severely high temperature. There we go, that was fine. But there I have a scar. Okay? This is gaining and releasing heat much faster compared to this. In this case, it's gaining heat very, very fast relative to this. Now, if we stop adding heat, it's going to release heat much faster compared to water. At home. Questions at home. Did I scare anybody when I did my little virtual heat up test and got my finger really scalded hot? Because of the low specific heat capacity of that iron. I'm blaming it on that physical property. Lance, you wake up? You're looking pensive? Okay. You're looking pensive. Which means quietly thoughtful. Next. Write thermochemical equations. So this is this is sounds like it's all fancy, but it's really just a chemical reaction, the typical equation. But we're going to add the enthalpy change to it. From this point on, just think of delta H as heat change. Delta H, enthalpy change, heat change, okay? Q and delta H from this point on, our own little exception was, well, internal energy, etc. But from this point on, delta H and Q are the same thing. Well, here's the reaction we did yesterday. CH4 plus O2 combustion. If it's complete combustion, so you're not getting any soot like pure carbon soot, like from a candle wax. It's kind of sooty, and but if it's complete combustion, you're going to get carbon dioxide, water. Let's make this liquid water. Let's balance this. And then let's put delta H. Delta H for the reaction, RXN, equals negative 890 kJs. So negative 890 kJs. And let's say kJs per mole, although we're going to talk about that in a moment. First of all, the enthalpy change, that's one of the things that makes this a thermochemical equation. So it looks just the same as a normal reaction that we've done. But now we've got the enthalpy change. In all thermochemical equations, it's essential that you indicate solid, liquid, or gas. So this is a gas, 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 and that's a liquid. So make a note of that. That's essential, that you have to have the states of matter there, because enthalpies change depending on what the states of matter are. Next, this is critical. We're going to read this enthalpy change as negative 890 kJs. Again, you guys realize negative means exothermic, right? Exiting, heat's exiting from the system into the surroundings, okay? But we're going to read this as, for every 1 mole of this that's consumed, you would get negative 890 kJs released. That makes sense, right? But this, what if we were talking about a different stoichiometric coefficient? If this is consumed, it's going to be negative 890 per 2 moles. Per 2 moles of O2. That's important, obviously. What about this? That much heat's released per 1 mole of CO2 produced. That much heat's released per 2 moles of liquid water produced. Okay? Now, usually at this point, I'd say everybody raise your hand if you think you're going to forget that and miss that on the first quiz. So raise your hand if you think you're going to forget that and miss it on the first quiz. Raise your hand at home if you're going to. Okay, who's that? There you go. Oh, I see you there, Grace Ann. Way to be honest. Braden said there's no way I'm going to forget that. And who's going to forget that? Don't forget that. Put your hands down. You're not going to forget that. Simple to remember. And let's do a practice. Okay? So let's say that this is in excess. Okay. And let's go with, we're going to combust methane with oxygen, and let's go with 20.0 grams of O2. How much heat is going to be released if, and remember, obviously that's limiting, so that determines the amount of product. Hey, you guys, look here. Limiting determines product. Only said that 15,000 times. But now limiting determines heat released, right? Here's the idea. 10 gallon of gasoline releases a certain amount of heat when it explodes. 10 gallons releases 10 times as much heat. Extensive property. Depends on the amount. Okay? Anyway, how much heat's going to be released if 20.0 grams of oxygen gas reacts with excess amounts of CH4? Go ahead, doer. Show work, show canceling. Ah, see that? That's deceiving. That's per 2 moles of this consumed. That's per 1 mole of CO2. You need to know what's going on here. This negative is a sign convention. On a different planet, they could have determined that we're not worried about the system losing energy, we're worried about the surrounding gaining, and they might reverse the sign conventions. Okay? So that's just a convention. It just tells you directional flow of energy from the system into the surroundings. Okay? If you get this question, it's actually useful to say this much energy is released by the system. Okay? Let's try another. Okay? Let me give you the reaction here. Plus O2 gas yields P4O10. Let's put a 5 here. And this is solid. Okay. Now let's look at the enthalpy. Right now, this is old-fashioned chemistry. So if I'm asking about a heat change, you don't know anything, right? Because you don't have an enthalpy change. So the enthalpy change is negative 3013 kJs. kJs per mole. Now notice you're going to read that as per 1 mole of this that's consumed, per 5 moles of this that's consumed, just like last time. Okay, per 1 mole of that. Now that's a high enthalpy change. You know, I just happened to be reading this morning about a little bit about, I'm a history guy, because at least I used to be, I read tons of stuff. And I'm interested in veterans experience, so we started myself and a friend of mine started a videography of veterans and their experiences. So we went around, we videotaped World War II veterans. There were like 6 different interviews, and they're all but guys over 90, but they're fascinating, unbelievable. Anyway, one of the things that the Germans did, they would use phosphorus bombs. Look at this. Phosphorus bombs, which would release huge amounts of energy. And they would explode these bombs over the foxholes of the Americans in Bastogne. So this is the Battle of the Bulge, Hitler's last-ditch effort to kind of turn the tide of the war. The Americans got surrounded in this small town in Belgium, I think it's Belgium, and they're trying to run them through and then make their way to cut off supply lines and some other things. But anyway, they would fire these bombs and they would purposely explode above, because these guys are dug down in small foxholes. They would purposely explode this above them. And with all this energy release, you get this gigantic firework. But this stuff would come raining down and burn right through 3 layers of clothes. So it was a scourge of the Americans that were trying to defend that small town. Anyway, look, my point here, look at the enthalpy change. Lots of heat released, highly exothermic. By the way, wasn't methane gas negative 890? So there's a reference, right? Negative 890 versus that. Okay, quite a bit more. Anyway, let's go with, let's say, let's go with 100.0 grams of O2. Excess here. By the way, you do realize that in the real world, this would be an excess, right? Why am I using this as limiting? Because I want to force you. So you people that raised your hand said you were going to forget that. I'm going to force you to use that coefficient in the solving. So how much energy is released in kJs? If this much oxygen gas reacts. People at home, the audio okay all the way through? Again, negative is a sign convention. Isabel, you going to forget this now? I did this quick. I need confirmation. What? Give me some numbers in kJs. Why am I? Let me do it again. Okay, so we have negative 1.883 kJs. kJs. The negative indicates energy is going from where the chemical reaction occurred to the outside world. So the outside world is heating up tremendously. What do you guys think? Is there a question here? Any questions? Let's look at people at home. People at home, any questions? It's essential that we get this stuff done, because then we can go to practice problems and kind of know what we're doing. All right. Well, everybody, I need to see a wave because my heart warms up. Okay, people live, wave to your friends. Be careful, social distance, 3 W's. Wear a mask. Watch your distance. What's the other W? Wash your hands. Have a good day, everybody.